Hey, today I want to show you an integral which we're going to solve by considering complex numbers and Feynman's integration technique. You could use brute force and deal with a particularly tedious and not very fun integration by parts, but hopefully the tricks I'll cover today could be of some use for an integral that you may one day have to deal with. First, let's use complex numbers to simplify this. If we look at the Taylor series expansions for cosine and sine, we see that one contains all the even powers, one all the odds, and both follow the same pattern of dividing by the factorial of each term's power. If we take a look at e to the x, we have the same pattern, but all terms have the same sign. We can group them together so that they resemble the Taylor series above, but for a difference in sign. Can we address it? Well, if we raise e to the power of ix instead of x, where I is the square root of -1, we see that we get exactly the pattern of signs that we need. The squared and the cubed terms are negative, but not the fourth and the fifth powers. Once we put everything together, this lets us write e to the ix as cosine x plus I sine x, where taking the real or imaginary parts of e to the I ax gives us back cosine ax and sine ax respectively. We can treat functions which only deal with real numbers as coefficients that we can ignore or factor out when we're taking the imaginary component of a product, like the one I've shown here. So if we return to the integral, we see that we can rewrite this as the imaginary component of the end result of a simpler integral. So x e to the power of minus bx sine ax becomes something that we can compress into just one exponential term. At this point, we could again do an integration by parts. It would be more straightforward than if we had used it at the start, but we can make one more nice simplification. If we let b minus ia equal c, the integrand becomes x e to the power of minus xc. Here we can use Feynman's integration technique, which involves node sync when an expression can be written as the derivative of another, which is like the opposite of what you typically think about when we're integrating something. In this case, we can rewrite this as the partial derivative with respect to c of minus e to the power of minus xc. We're treating it as if it were a variable rather than a constant. A partial derivative acts in the same way as a normal derivative, but it treats all the other variables in the function with differentiating as if they were constants. So we can write the integral as this, the imaginary part of a derivative of an integral, which is a cool situation where we've used a load of different operations to simplify things. The integral is now pretty simple. It treats c as a constant and it integrates as usual, giving us 1 over c e to the power of minus xc, and the bounds mean that we're left with minus 1 over c. So the derivative will just be 1 over c squared. We can now substitute in b minus ia to start rearranging it to make clear that the real and imaginary components are what they are. We want to get rid of the I term in the denominator, and we can do this by multiplying the top and bottom by b plus ia to the power of 2. Once we simplify this, we see that the denominator is now exclusively real. Next, we can expand the numerator's brackets and can now clearly see that the imaginary component in the expression is 2ab over b squared plus a squared, which is the answer to our integral.